Hello and welcome to our pre-calculus topic 1 formative 1 uh, progress check review for today's date is October 28th. So I'm going to be running through each of the formatives for reviewing for the progress check of 2018 marking period 1. So we're going to start by working with a formative assessment. Calculators are allowed for these. So piecewise function, composition of functions, 24 points. So I'll be going through the correct answers and then kind of more of an explanation on why those are the correct way that they are. So let's just get started. So number 1 says, which of the following are bounded below? Check the two that apply. So now when something is considered to be bounded below, it is referring to when I have a specific type of graph and the graph never actually goes to, let's say, negative infinity. So in this example, right, I see that the graph never actually goes down further into kind of the south region, the negative region in terms of the graph. So we could say that that graph is bounded below. So if we look at the first one, this is actually a linear equation. So it's top left to bottom right. So that one actually goes down below. So that is not bounded below. We take a look at ln of x. ln of x has a particular graph that goes like this, right? But it actually still goes down to negative infinity, so that one is out as well. So our two choices are actually going to be the last two that are really going to be bounded below. So this right here is an absolute value function. It's denoted by the two bars right here. This means it's translated 2 units to the right and then 1 unit down. More specifically, we know that it creates a V shape, just like this. And we notice that the graph never actually goes down to negative infinity, so it is considered to be bounded below. So that would be one of our answers. Now the next one is 1 over x squared. Now if you get lost in trying to figure out what this value might possibly be, you can always plug in values in a table, so x and y. So if we try placing in, let's say 0, we get an undefined. So we know that there's going to be some type of vertical asymptote at x is equal to 0, more specifically since we can have a 0 in the denominator. If we end up choosing -1, we get 1. If we choose 1, we also get 1. So we end up getting a graph. We know we have a vertical asymptote, and we know we have a value at 1, 1, and -1, 1. Now, as the values start to get a little bit larger, so 2, 3, and 4, we'll notice that this actually ends up becoming 1/4 and 1/9 and 1/16. So we can see that the values are getting smaller each time. So it ends up looking something like this. And then since it is squared, it also is going to give us positive y values for the other side. So we also know that with a vertical asymptote, the graph gets infinitely closer to that specific value. So what's going to end up happening is it's going to look like this. Now, yet again, you can always plug this value into the calculator and just assume, trying to figure out the values from there. So the graph doesn't reach down below the negative, so I'm going to go with that is also bounded below. Now, just because it doesn't hit any parts in the negative does not necessarily mean that it is bounded, right? So I could end up having something that looks like this, right? Even though like it does touch a little bit down in the negative, right? This is still considered to be unbounded. We can also assume something that looks like this, right? If this is, let's say, in the negative, right, we still do not have y values that go down to negative infinity. That's technically what we're trying to look for these. Okay, so number 2, it says, which of the following graphs below are 1 to 1? So 1 to 1 really means that the inverse is a function and the original one is also a function. So we're already stating that it is already a function. So that means it passes what we call the vertical line test. Okay, so what that is, that means that if we have a line that comes across vertically, that it will always just hit the graph once or maybe not at all. But if it hits it twice, then it is considered to be not a function. So all of these are actually all functions. But whether something is actually going to be 1 to 1 or mean that the inverse is actually going to be a function, that means it passes the the horizontal line test. So the horizontal line test works the same way, but you'll notice right here that it hits it at 3 points. If it hits it at more than 1 point, then it is considered to be not 1 to 1. So therefore, this is actually the opposite, right? That would not be 1 to 1. Same thing with this one. This would not be 1 to 1 because it does not pass the horizontal line test. So which ones that are 1 to 1? This one and this one. Okay, moving on. So it says if f of x is equal to 3x squared minus 9, compute and simplify if f of negative x is determined whether f is even. So f being even would mean that if I take the negative x and place it into my function f, I should actually get back out the original. So which means that the negative actually has no effect on the graph itself. So if I end up doing this, right, f of negative x is equal to 3 parentheses squared minus 9. So how we do this problem is we always place in whatever's inside f. So we're going to place in let's say a negative x. Now with this done, we end up getting, well, when we do negative x times negative x, because this is squared, we actually get a positive x, so which means that the negative does not actually come out. So we're going to be left with 3x squared minus 9, and we double check to see if that gets us back to the original. If it does, then yes, this is even. Move on. So it says suppose f of x is going to 7, as x is going to 4 from the right-hand side. Then it says f of 4 is equal to 3. It says f has a removable discontinuity at 4. So what that means here is that f has a removable discontinuity at 4. So 1, 2, 3, 4. So at 4, that means that there is going to be some type of hole. So if I take a look at this, I'm going to have a hole. And I know that for this specific part right here, it says if I'm looking at it from the left-hand side, so that means I'm heading this direction, from the right-hand side, this is going to be going to 7. So 7 is going to be up here. Now it says f of 3 actually is going to be, let's say, down here at this specific point. But since I know that it is a removable discontinuity, that means I know this curve actually continues right from that 7 spot. Now I don't necessarily know if it's going up or down, but that really doesn't matter. But I do know that from the other side, this is also going to 7. So it's going to 7 from the right-hand side and also from the left. So that means from the left-hand side, as x is going to 4 from the left-hand side, y is also going to, and this is going to be 7. And more specifically, because it has a removable discontinuity. Now the next one says it has a jump discontinuity. So that means that it's not just going to be a hole, but it's going to be something sort of like this. So I'll put in kind of the same information. So 4, I'm going to have a hole. And then from the right-hand side, right, that's what that plus means. From the right-hand side, as it's coming up, is going to 7. So 7 is right here. And then we still have 4 comma 3. So that means that there's going to be a point here. So x is going to be equal to 4. So if x has, or then as x goes to 4 from the left-hand side, so that means that they're trying to figure out, is it going to actually 7 or is it coming to 3? But since we say that this is a jump discontinuity, that means that it is not going to start from there, right? It's not actually going to be from there, because if it was, it would be considered to be removable. So that is actually out. So it can actually be from 3, or it could actually be any other type of location, right? It could be any type of location coming from that same type of value. So really, most people would probably end up saying just kind of 3, but really any number is correct with the exception of 7. You just cannot say 7. Kind of a bummer. Okay, so when we're talking about these piecewise functions, right, they can get very, very confusing. But what ends up happening here is if I want this graph to be confusing, that means I want them to have the same y value. So I want y is equal to x squared plus 3, because really this is just saying I have two different equations, and they are two different parts that are actually organized for the graph. And I'm going to go into more detail about how to actually graph that for number 7. But for the most part, they're really just saying two different equations. So y is equal to x squared plus 3, and y is equal to 3x minus a. And I'm trying to figure out what is the a value that is going to allow me to, in a sense, have this graph have the same y value. Well, if I know that I want the y values to be the same, I'm just going to actually set them equal to one another. So I'm going to say 3x minus a equals x squared plus 3. Now, I also notice the x value is located at 2, right? So I do not even care if it's going to be less than or equal to or greater than or equal to. That really doesn't matter. The only thing that I need to know about this is that the switchover is at x is equal to 2. So what I'm going to do here is for every single x value, I'm going to actually set it equal to 2. So 3 parentheses minus a is equal to parentheses squared plus 3, and place in that 2 value. So I end up getting 6 minus a equals 4 plus 3. I get 7 is equal to 6 minus a. If I subtract 6 to both sides, I end up getting negative a is equal to 1, and therefore a is going to be equal to negative 1 if I multiply or divide both sides by negative 1. So now just to double check my answer, what I can do here is I can say x squared plus 3 is equal to y, and then I'm checking for x is equal to 2. So I end up getting 4 plus 3 is equal to y, so that means that that value is going to be equal to 7. Now, even though it says less than, which means that this value technically does not exist, right? There is actually a hole at that value. I'm going to just check it for the other one. So I'm going to say 3x, and then I know that my a value is going to be negative 1, because I'm checking this right now. So I'm going to say 3x plus 1 is going to be equal to y. I'm going to place in that 2 value just like I did for the other equation, and I end up getting 7 is equal to y. Now, do they have the same y values? Yes. Then I know that I got my a value correct. Do you need to do this check? No, but it's nice to just kind of confirm your answer is correct. Okay, moving on to number 7. Now I'm going to break down systematically how I organize these types of problems. You might have a method that works well for you. That's great. That's fantastic. If you get completely lost when you deal with these types of problems, I'll show you systematically how I go about approaching these. So the first thing I do is I organize writing down what each one of these equations are in terms of the piecewise. So this is my first equation, this is my second equation, and then my third equation. The next thing I do is I draw kind of a quick sketch about what these graphs are technically going to look like. So the first one I know, since it has an x squared, I'm going to make it so that it is a parabola with it almost making a smiley face, because I know the x squared is positive, so that I know it's the vertex is going down while the arrows are going up to infinity. The second equation, number 2, is actually a horizontal line actually at 2, because if it was just y is equal to 2, it would be a horizontal line. And then the last one is a square root function, so it is going to look something like this. So just so I have an idea about what the graphs look like, the next thing I'm going to do is I'm going to organize them actually on the graph. Now, I'm going to be putting in vertical lines that are dotted, but they're not vertical asymptotes, just so that you don't get confused about what is what and such. So I'm going to use 0, and I'm going to be using 3. So at 0, I'm going to place in a dotted line, and I'm going to place in a dotted line also at 3. Now right at the top, I'm going to take a look at each one of these. So it says x is less than or equal to 0. I'm going to place in the equation number 1 right there. I'm also going to include kind of like a picture to go along with it. So that's what I want it to look like in that specific section. I don't know how perfectly it's going to align, but we'll figure it out from there. So in the second one, number 2, this is going to be a horizontal line. And then number 3 is going to look like that dot, the square root function. Now the next thing I'm going to do is I'm going to work on x is equal to 0, and then x is equal to 3. Now there are 2 options for this. What I focus on for x is equal to 0 is I'm working on looking at this right here. So when it says x is equal to 0, that means that it is going to make an actual dot. So I'm going to be using equation 1. Now when it has less than or equal to, that means it's going to form a dot. If it has just a less than symbol or just a greater than symbol, it's going to form a hole. So I'm going to say at x is equal to 1, it's going to form a dot. So that means that, or I could also call that a point, right? I'll just say point as well. So I'm going to place in 0 squared minus 5 into that first equation. So I'm going to get negative 5. So that means at the ordered pair 0 comma negative 5, I'm going to actually draw that point. So at 0, negative 5, I'm going to place that point. And remember, it said since from that first equation, I can kind of finish up the parabola stuff, but I'll do that a little bit. So for equation number 2, that's actually going to form a hole. So that's kind of really nice. That's just at 2 because it's a horizontal line. So at 2, or more specifically 0, comma 2, that's going to form a horizontal line. Now I'll actually finish that one up right here because it ends up forming a horizontal line. Now I just don't know what happens at 3. Actually, I do. I can see right here. This is actually going to form a hole at equation number 2. But actually, it forms also a hole at equation number 3 because this one has a greater than symbol. So there's actually going to be 2 different holes that are going to end up happening here. So I'm going to end up having a hole at 3, comma 2. So that's going to be a hole at 2. And then for equation number 3, when I place in square root of 3 plus 1, that's going to give me a 2. Now that's also going to just be another hole on top of a hole, so it never really actually fills in, which is interesting. Anyway, so from here, I don't know what the left-hand side of the graph is right over here, but I do know that it looks like a parabola. So what I can do here is, since I'm talking about values that are on the left-hand side, I can start plugging in values. So -2, or excuse me, -1, -2, -3, -4. What those are going to do is these are going to be used for equation number 1 and figuring out what this graph actually looks like. So I can think about this as -1 squared minus 5, which ends up giving you 1 minus 5, which gives me -4. -2 squared minus 5, which gives me 4 minus 5, which gives me -1. -3 squared minus 5, which gives me 9 minus 5, which is 4. And then -4 squared minus 5, which gives me 16 minus 5, which gives me 11. Now I'm probably not going to go up to 11, but that's okay. So -1, comma, -4. -1, -4. I have -2, -1. And I have -3, 4, and I'll probably just kind of finish from there. So I can see that that's going to be kind of that side of the graph being a parabola. Now the middle one, right, it's just horizontal, right? So that's just fine. I don't need any fancy graphing for there. I'm going to choose another set of tables, or another set of values. So I'm going to choose ones that are going to be on the right-hand side of that 3. So I'm going to choose 4, 5, 6, 7, and 8. And this time I'm going to be using equation number 3 for this. So I'm going to say square root of 4 plus 1. Well, that doesn't give me anything kind of nice, right? That gives me square root of 5. Let's try the next one, 5 plus 1. That gives me square root of 6, nope. Square root of 7, nope. Square root of 8, square root of 9. Okay, that one gives me a nice one. So that's going to be 8, comma 3. So at 8, I'm going to place a value at 3, and I know that those are going to connect to make kind of like that nice curve. So this is technically my graph that I have available for me. So a couple things, as x goes to negative infinity, the y value is going up to positive infinity, so that would be positive infinity. As x goes to positive infinity, it is also going to positive infinity, so infinity, infinity. From the left-hand side, that's what that negative means. From the left-hand side, I'm going in this direction. As I'm getting closer and closer to 0 from the left-hand side, I'm getting closer and closer to -5. From the right-hand side, I'm looking at it getting closer and closer to 0. That's getting closer and closer to the number 2. Now, I'm not really concerned with the actual value that is at 0, right? There is a value at 0, -5, but that's not what it's really asking you. It's saying as it approaches 2, or as it approaches 0 from the right-hand side. Now, x is equal to 3. Or excuse me, as x approaches 3, right? We can see that it approaches 3 from the left-hand side being 2. We can see it approaches from the right-hand side being 2. So my answer is actually going to be 2. When we don't see a plus or a minus sign, we actually have to check for both. So if it's both approaching from either side, and it ends up becoming that same value, then we say that that has what we call removable discontinuity. Okay, moving on. So it says a car manufacturer advertises its new car goes from 0 to 60 miles per hour in 3 seconds based on a driving test. During the first 3 seconds of the test, was the car's speed ever exactly 30 miles an hour. So in this case, this is actually going to be true. So when a car is at rest, for example, right, it's at 0 miles per hour, right? It just can't magically just jump straight to 60 miles an hour, right? It runs through each one. And as we see the speedometer kind of start to grow, when we see, right, the speedometer, right, it starts to change each time as you're starting to go faster. And eventually what will end up happening is it will hit that 30 miles an hour. It might not stay there for very long, but it does end up hitting it. Now there is a calculus-based concept for this. This is called the intermediate value theorem. You do not necessarily need to know what that name is, but what that means here is that if I end up having, let's say, 2 points, and that are what we call continuous. That means that if I have, let's say, an A and a B value for my X values, and this is, let's say, f of A, and this is f of B, that means that if f of A and f of B are at different heights, there's any number of values that are going to be some type of Y value that are going to be in between those. It will always hit a value that is in between f of A and f of B. And that will also yield some type of C value. Now that might be kind of confusing for you, but in the terms of driving for a driving test, right, we will always end up hitting all the miles per hours before we actually hit 60, right? We'll hit 2, 3, 4, 5, 6. Might not be for very long, but we always hit it. So now, number 9, it says, let f of g of x be equal to that equation. So without using the identity functions, write the possible rules for f and g of x. Now the thing that I noticed right here is that these values are exactly the same. So this x minus this x minus 2. So it looks like that x minus 2 gets placed into another function. So if it gets placed, it looks like that that's going to actually be g of x. So I'm going to let g of x be equal to x minus 7. Now, once I do that, I'm going to take a look at just removing those and just calling those x. And if I just call those x, because I'm actually doing the opposite of what we call the composition functions. We're decomposing, so to speak. It's just going to be those specific values, but instead of replacing the x minus 7, we're just going to call that x. So it's going to be 5x squared plus 2x minus 11. And there's your answer. Lastly, and I think this is the last problem for the page, it says consider the function f of x is equal to x to the third plus 6 and g of x is equal to cube root of x minus 6. Find the rules of f of g and g of x g of f of x to show that f and g are inverses. So how you show that? So f of g of x, which is also another way of writing f o g of x, and then g of f of x. Now, depending on your specific teacher, some teachers might require you to do both of these. So, and I just wrote the same thing. So this is going to be g o f of x. And what I'll do is I'll actually show both of these. So I'll start off with f of g of x. So the first thing I do is I write f and then whatever g is going to be. So that's going to be cube root of x minus 6. And then we're going to write f of x without the parentheses. So I'm going to write x to the third power plus 6, right? And isn't that technically what f is? So what I'm going to do here is I'm going to place in g of x, which is that value, right into that parentheses. Now what ends up happening with these, so I have a cube root and a cube, they cancel with one another, so I'm technically left with x plus 6, x minus 6 plus 6, which ends up giving me x. That's a good sign, so if I end up getting an x value, that means that they are inverses. So I'll do the other version, so g of f of x. So it's going to be g of, I'm going to write f of x, so that's going to be x cubed plus 6. Is equal to, so we're going to write the cube root, parentheses, minus 6, and I'm going to place in my f of x, which is going to be that x to the third plus 6. Now, since there's nothing actually being applied to this parentheses, actually I can break that out. So I'm going to actually write that as cube root of x to the third plus 6 minus 6. And I end up getting, right, those two cancel. I get the cube root of x cubed, which is ultimately going to leave me with x. So if I'm left with x, then I can say that these two, in a sense, functions are inverses. Also, I can write this as f of the inverse of x, right? And if we actually do the composition of both an original function and its inverse, they technically cancel each other out, and you're only left with x. So I hope you guys found this informative. Please comment down below if you guys have any other questions, and thanks for watching.